This is example 4 for optimization, and we're going to look at trying to optimize cost, which is something that makes sense that we would want to be able to do. So before we do that, I just want to make sure that you realize what the sort of overall steps are when you're trying to optimize a problem. And depending on what you're given, the way these steps look is going to be different, but you want to kind of keep them in the back of your head. So the first thing you want to do is determine what it is that you are trying to optimize. So there's always something, and once you determine that, you need to find an equation for what you're trying to optimize. For all of the more challenging optimization problems, this equation will have more than one variable in it, and we need only one variable. So we will need to figure out a way to rewrite the equation using only one variable instead of 2 and possibly 3. And finally, once you have the equation with only one variable, you've done most of the problem solving. At this point, you are just going to find the derivative and set it equal to 0, which will give you the turning points. So it will give you the critical numbers, so the optimum places. So if there are more than one, you would pick which one makes the most sense. But often, there will only be one value, and that's the one we want. So these are our 3 basic steps. Determine what you're trying to optimize and generate an equation. Rewrite the equation using only one variable, and then find the derivative and set it equal to 0. And you should be able to solve the problem from there. So let's look at a specific example here. We have an open-top storage box with a square base with a particular capacity of 5 meters cubed. We have different costs for the different parts of the box. So the sides are $1.60 per meter squared, but the bottom is $2 per meter squared. We want the dimensions that will minimize the cost. So anytime you see a question like this, you need to be able to figure out what it is you're trying to optimize. So in this question, we're minimizing cost, so we are going to find an equation for cost. That's our first step, is trying to figure out an equation to represent the cost. So if I were doing this problem myself, the first thing I'd probably do is draw a little diagram. So in my little diagram, I have my box that has a square base. So because the base is square, whatever letter I want to use to represent the length, I can use the same letter for the width. So we've got 4 sides here, they're all x, and the surface area of the bottom there is x squared. We also have 4 sides, and we don't know how high the box is. So we have to use a different variable here. So each of the heights are going to be y. You can use any 2 letters you want. You could have put the x in the opposite spot. It's going to work out no matter what, as long as you understand why I put the letters where I did. So the bottom is a square, so we get x and x, but we don't know how high it is. We don't have to worry about the top, but that'll come in a second. So now we're going to come up with an equation for cost. So right off the bat, we know that cost is going to be a function of some variable, and I'm choosing for it to be x. But let's say we didn't know that. We're going to take away this part, and we're just going to say, all right, let's get an equation for cost. We know that the bottom is $2 per meter, so we're going to multiply 2 by the surface area of the bottom and add to that $1.60 per side, and the surface area of the sides. So we're going to multiply $1.60 by the surface area of the sides, but there are 4 sides we have to worry about, so we're going to have 4 times the surface area of the sides. And that will give us the overall cost. So we can start putting variables in here. $2 times the surface area of the bottom. The surface area of the bottom is going to be x squared times plus $1.60 times 4 times the surface area of the sides. Each side is going to have a surface area of x times y. So we end up with this equation, which is helpful. So we have our cost equation, but we are not ready to get the derivative yet because of this second variable. So we need to write this whole equation in terms of just x or just y. And it doesn't matter which one we choose. Often in optimization questions, this is the tricky part, trying to figure out how to relate the two equations to one another. So we only want one variable, and there will always be enough information in the question to rewrite the equation with only the one variable. So we've been told that it has a capacity of 5 meters cubed. So that's the piece of information that's going to allow us to get rid of the y there. So the fact that the capacity is 5 meters cubed is actually telling us that the volume of the box is 5. Based on the variables we chose, we can represent the volume as x, so length times width times height. So we can represent the volume as x squared y. We're going to use this equation to get an expression for y. So isolate y, and then come back into our cost equation and replace y with 5 over x squared. And once we've done that, we will no longer have two variables. We'll only have the one. So now we have our cost equation in terms of only one variable. So instead of just writing c, I'm going to write c at x. And we can simplify that a little bit before getting the derivative and setting it equal to 0, just to make our life a little bit easier. So we can put some things together here. We're going to end up with 2x squared plus 32 x to the power of negative 1. You could have left it as 32 over x. It doesn't matter. Either way, when you go to get the derivative, it's going to be fine. So now we have this cost equation. The next part is actually pretty straightforward. We're just going to find the derivative of this equation. And set it equal to 0. And solve. So in order to get the entire dimensions, we also have to solve for y. We already had an equation on the previous sheet where we said y was equal to 5 over x squared. So y is going to end up being 5 over 4. So the dimensions are 2 by 2 on the bottom and 5 over 4 along the sides. And we should probably put in, I think these are all in meters. The last thing we need to do quickly is answer the second part of the question, which said, what is the minimum cost? So if we go back to our equation that we had for cost, we said that cost is going to be 32x to the power of negative 1 plus 2x squared. And we said that the minimum is going to occur when x is equal to 2. So we can just plug 2 into that equation, which gives us a minimum cost of $24. And that's the end of this problem.